What if you could generate powerful quantum resources without using complex non-linear optics, simply by tweaking the shape of a potential? This paper investigates whether isospectral oscillators can serve as a new fuel for quantum information processing. To understand why this is necessary, we first need to look at the limitations of our current standard tools. While Gaussian states are the workhorses of continuous variable systems, they hit a hard ceiling because they cannot perform universal quantum computation on their own. Generating the required non-Gaussian states usually demands expensive hardware like photon counters or complex nonlinear processes. The researchers propose a clever workaround that focuses on the static hardware rather than dynamic processes. They utilize a framework called SUSY Q meters to design new physical potentials that share the exact same energy levels as a standard oscillator. These isospectral partners provide a way to change the shape of the quantum state without tearing up the familiar energy ladder. By applying a mathematical deformation controlled by a parameter lambda, the authors transform the boring parabolic potential of a shifted harmonic oscillator into a complex, anharmonic shape. This structural distortion forces the ground state to stretch and squeeze, naturally becoming non-Gaussian. With the theoretical framework in place, let's examine the specific resources these deformed potentials can produce. The study confirms that these deformed oscillators act as generators for key quantum features, specifically Wigner negativity and quadrature squeezing. As you ramp up the deformation lambda, the system inherently produces the kind of negativity in phase space that signals true quantum advantage. Perhaps most surprisingly, these delicate quantum properties don't just vanish when you turn up the heat. The authors show that non-Gaussianity persists in thermal states, and in some specific configurations, higher temperatures actually enhance the quantum features. While the deformation adds value, measuring it comes with a trade-off grounded in the quantum Fisher information. A simple position measurement is optimal for detecting the deformation, but the precision of this estimation actually decreases as the potential becomes more distorted. This work establishes isospectral oscillators as a viable, static platform for continuous variable quantum information, reducing the need for active nonlinear optical controls. It turns out that simply designing the right container for your quantum state is enough to unlock powerful computational resources. To learn more, head to emergentmind.com.